Good morning to everybody. I'm delighted to be part of ACP 2020. It's regrettable that I'm not there with you in person. I love visiting Beijing. The last two visits were memorable, but unfortunately this year is very strange. And so I'm glad I'm able to make this remote presentation, and I thank the organizers for kindly inviting me and allowing me to present our lab's work. So I come from the Indian Institute of Technology, a 10-year-old institute in the western part of the country. And here we are. It's a very nice campus. And we have a reasonably nice set of activities going. So allow me to present my work now. Sorry. Okay. Our work has these four areas, and all of them use the semiconductor laser quite heavily. But today I'm going to talk only about the high sensitivity trace gas measurement activity using quantum cascade lasers that has been led by Dr. Anirban Roy, who recently graduated from our lab. Okay, why do we want to do this? So here is the content of the talk. We'll talk about the high sensitivity, the need for such measurements. We'll review the WMS technique. We'll introduce the concept of calibration-free measurements that will allow me to then talk about the specific technique that we've just introduced, and we'll show you demonstrations of actual field measurements with that technique. And then I'll draw the conclusions and hopefully convince you that this method has some merit. We need to do a lot of measurements in India because we have a lot of pollution. We have a lot of industrial activity, in particular in the state that I live in, that has a lot of pharmaceutical, oil and gas activity, and textile-based activities. And these produce a lot of emissions, and these need to be monitored. The other aspect of industrial activity is the chances of accidents. And we've had many such accidents over the decades. The most prominent one being in 1984, where thousands of people died due to a leak in a gas factory. And then there was no detection, there was no preemptive steps that could be taken at that time. But the situation is still worrying in 2020. So there was a recent accident in Vizag, southern India, where people died because of a leak. So such activities require high sensitivity monitoring around the clock. The governments are trying to do their best, but the number of monitoring stations that are available is not very large. So there's a lot of what we call spatio-temporal gaps that need to be filled. And laser spectroscopy is a very, very good candidate. Apart from those industrial activities, there is also the greenhouse gas measurement work that goes on. The Global Atmospheric Watch has many stations in India scattered around the country. And there are labs that are carrying out these measurements in various parts. But as you see from some of these writings, the situation is not as good as it can be in terms of both in terms of the techniques that people use and also in terms of, again, the spatial coverage that's possible with bulky and sensitive systems. So there is scope for bringing in WMS using quantum cascade lasers, that you can make them small, portable, rugged, and you can make a large deployment. You can deploy them over large areas, and you can make a network of monitoring stations that can give you a much better picture of what's going on across the country. So that is where we want to come in. The very basics of the technique need to be reviewed. So here we have a molecule that likes to vibrate, oscillate at certain frequencies. And if you can shine light of that specific frequency, the molecule will absorb that light. And every molecule has a characteristic signature. So if you can pick out one of these absorption lines selectively, hopefully in the mid-infrared region where molecules absorb very strongly, then you have a very good chance of performing high sensitivity measurements and detecting trace gases. Of course, the problem with the mid-infrared is that although it has very high sensitivity, there is also a lot of spectral overlap, as is obvious from this picture over here. And so if you zoom in, and if you look at carbon dioxide, for instance, absorbing between 1998 and about 2003, 2005 nanometers, we see that there are a couple of lines of carbon dioxide that you can still pick out in the presence of water vapor and other gases. I've chosen ammonia over here. So it is possible to identify a single isolated absorption line in certain conditions, and then be able to only measure that particular gas while ignoring any other pollutants that may be present. But that's a matter of engineering judgment, and the um, actual scenario will have a lot to say about that. But that's the general idea. But direct detection, where you simply shine light like that and place a photodetector on the other hand, on the other end, is not very sensitive, although it is very simple. So that is why people have moved into the area of wavelength modulation spectroscopy, which is a much higher sensitive, much higher sensitivity. It offers much higher sensitivity. Sorry. The basic scenario is you have a laser and you have a detector, and there is gas in between. So here is the gas. This is an open path measurement that we've considered here. The laser is modulated with a signal generator. Its wavelength is scanned slowly, but in addition to that, there is also a high frequency modulation that is superimposed. So when you superimpose a frequency modulation on the light, that frequency modulated light interacts with a single absorption line of a gas, and you get signals at various harmonics of the modulation frequency. And the shape of these harmonic signals is given by the Fourier coefficients, Fourier expansion of the absorption line itself. So each of these harmonic signals, the 1f, the 2f, etc., they are uniquely related to the absorption line itself. Now, so far, the story was quite nice. But unfortunately, as you modulate the current of the laser, you also modulate the intensity of the laser. And this intensity modulation has a linear as well as a nonlinear component. So these are the amplitudes, del I1 and del I2, but they're also offset from the frequency modulation component by phase differences that are unique to the laser and unique for the modulation frequency that you choose. So overall, all in all, what you have is what we call a game of shadows, in that the intensity of light that you finally record using the photodetector is a combination of an intensity modulation component and a component that comes from the gas. So here is a laser contribution, and here is the gas contribution. Unfortunately, a given harmonic cannot anymore be detected in isolation from the contributions from the other harmonics. So that is depicted in this phase diagram, where in this case, we have chosen the first harmonic signal. So the first harmonic signal is what we want to detect, which is given by the red arrow. And you see that it is scaled by the intensity of the laser. Unfortunately, that is not the only component, because the intensity modulation of the laser, both the linear as well as the nonlinear components, they bring in additional components that would be projected onto this detection axis. And each of those projections bears the shape of the lower harmonic and a higher harmonic. I'm sorry, this should have been H2 over here. So the lower and the higher harmonics also now begin to cast shadows on the main harmonic. And the same goes for the second harmonic detection as well. So the lower harmonic and the higher harmonic comes in and contributes shadows, and those shadows are scaled by the intensity modulation of the laser. In most cases, the linear intensity modulation is much stronger than the nonlinear component. So in most cases, it is sufficient to consider the red and the blue signal components. The green ones are typically weaker, but again, that would depend on the laser. So all in all, what you get is, if you wanted to detect the second harmonic signal, you would have expected to recover this red, nice and symmetric signal. Unfortunately, the, the green and the blue that correspond to the higher and the lower harmonics, they come in and cast shadows and distorts your second harmonic signal. And what you end up with is the magenta curve for this given laser. So it is important now to be able to incorporate these distortions into the model that you develop for the second harmonic signal. So it is no longer sufficient simply to obtain the second Fourier coefficient and try to extract gas information. That situation is depicted mathematically, again, where the red one is the quantity of interest. It is scaled by the first harmonic. It has the shape of the first harmonic and scaled by the intensity. So if these other distorting factors had not been present, you could simply divide the signal that you receive by the intensity of the laser, and you would be back to the first harmonic, the pure first harmonic shape. And that can be you can easily extract the mole fraction and the pressure from it. But unfortunately, these blue and the green distorting factors also come in, and we need to account for these. In a similar fashion, for the second harmonic also, you get an expression. And these signals are detected along the two orthogonal lock-in axes. But if you take the modulus of that, then you can get rid of the lock-in phase setting, which is very difficult to do. So typically, one uses the magnitude signal of a given harmonic signal. And so you have an experimentally obtained magnitude signal, and if you have a simulated version of the magnitude signal, you try to match them with the laser, the mole fraction and the pressure as free parameters. And once you get a good fit, you can infer those quantities. So that's been the approach for a long time. Of course, you need to take into account the laser behavior, the behavior of the wavelength tuning characteristics and the frequency modulation characteristics of the laser, the phase difference, and the tuning parameter, which tells you how frequency agile these lasers are. And as you see that the variations are not, you cannot ignore the variations that you see across the wavelength scan range. So each laser modulated at specific frequency will give you a certain behavior, and this behavior needs to be known and taken into account in the simulation of the harmonic signal that you ultimately want to generate. The calibration-free techniques have come in a big way for the simple reason that the signal that you detect on the photodiode varies due to two reasons. One is if the gas itself changes, the mole fraction changes or the pressure changes, then the signal is bound to change. But on the other hand, if the gas composition and the gas conditions don't change, but you have variable coupling between the laser and the detector, or maybe there's dust gathering, or there's spurious misalignment of the laser from time to time, your intensity signal would still vary, even if the gas signal did not vary. So it is important to be able to ignore or take into account those unwanted variations so that you can reliably measure what you want to measure. That's the information that the gas gives you. So to do that, primarily there have been two approaches. One has been a first harmonic approach, which is the RAM and the PDM approach, in which the line shape itself is directly recovered, as shown in this figure. It is a first harmonic WMS approach, but it does not use the first harmonic line shape. It directly recovers the absorption line shape. And in this respect, it is very similar to direct detection, but it suffers from poor signal to noise ratio. The most successful calibration-free technique has so far been Greg Rieker's version, where the magnitude of the 2F signal is divided by the magnitude of the 1F signal, and a relationship between those two signals has been shown to be very robust to these variations, unwanted variations. And they've, as you see, they've applied it to very complicated scenarios. Of course, that technique requires the laser parameters to be pre-characterized and fed into the model. There was some work that was demonstrated in our lab a couple of years back, and also in collaboration with another lab, where we showed that the laser parameters can be obtained directly from the spectral wings, and so a pre-characterization was no longer necessary. And we also showed that that technique can be applied to QCLs, VCSELs, edge-emitting lasers. So that was a nice piece of work. A very recent, slightly different approach has been a 1F approach, where the magnitude of the 1F signal was divided by one of the lock-in axes signals recovered on the y-axis of the lock-in signal. And it was shown that the 1F signal that you generated by this method performed very nicely in an industrial setting where there was a gas turbine. And they've also compared the performance with the 1F by 2F method that is shown over here. It is expected that the 1F approach would give you higher signal-to-noise ratio and therefore lower detection capabilities, because the 1F signal is always stronger. However, this has been so far demonstrated for very large mole fractions, 100% CO2 in this case, which is not likely to be a realistic scenario in many cases. So there is also some scope for improvement. The thing with these two techniques is the signals appear on a background, and that background has to be accounted for. So this is where we come in, and we came across, this idea struck us that if you look at a typical WMS TDLS setup, the details of these boxes are not that important. The only thing I'm trying to show over here that there are many parts within a system where you could be making measurements. Now, if you measure the intensity of the laser over here at this point, at these points, and if you plot them, you see that the intensity shows quite a lot of variation. For instance, the red one and the blue one, these two are at the output of a 50-50 coupler, and so they're reasonably similar. But once that light goes through a gas chamber, and you look at the green intensity, that shows a huge difference. So the intensity varies because there's a lot of coupling issues in between. So the point is that the intensity at different points within a system could vary, and likewise the intensity modulation also could vary. However, the surprising thing was, if you take the ratio of these two quantities, that shows remarkable stability. So this curve is the ratio at those four places. So you see the individual variations are huge, but the net ratio does not vary at all. So del I by I becomes a system parameter. So if you can modify the math and reduce everything in terms of del I by I, or I by del I in this case, then you have a robust invariant quantity within your measurement, and you can achieve calibration-free measurements. So that's what we show over here by doing the math. The R1F by del I1 has that expression where these ratios appear here and appear there, and H1, H0, the H's are the Fourier coefficients, which are easy to calculate. So if we do this for a real-life measurement, this was ambient CO and CO2 measurements. You see again the baselines that give you the intensity modulations. They're also varying quite a bit. The intensities vary. So here is the intensity variation, and you can see the intensity modulation variation. But if you take the ratio again, this is rock solid. And this is over a period of several hours, which is very pleasing. You can do the same thing for the nonlinear intensity modulation, which would be relevant in this case. And there too, you see that the intensity varies, but the intensity modulation, the ratio of I to del I2 does not vary, and the ratio of the intensity modulation components themselves do not vary. So you have these components that are rock solid. And so your measurements will appear on a background of precisely 1, and you can avoid the variation of the detector gain with modulation frequency if you operate at a single frequency. So like over here, if you're operating at a single frequency because you're doing del I1. That is where this has an advantage. So let's look at some of the results. We looked at the mid-infrared, and we were looking at CO and CO2. So here is the line that we chose in the mid-infrared. We used 2 QCLs to target these 2 absorption lines. And here is the block diagram of the actual setup, where we measured the intensity and the intensity modulation components at this point, right at the output of the laser before it interacted with the gas. The ratio over here will remain the same as the ratio calculated in other places. And the signal at this point is this blue signal that has the ramp and the sinusoid superimposed on it. So if you digitally filter it out, you can obtain the 1F signal component, which looks like this. That's a sinusoid. And if you apply a bandpass filter, you can filter that out. If you use a low pass digital filter, you can filter out the ramp signal. So you can get del I as well as I. You can get the ratios. You can therefore use those previous formulae. And here are some examples of ambient CO and CO2. And I draw your attention to the concentration levels. This is about 500 parts per billion for carbon monoxide. Single pass measurement with a path length of 4 meters. Very hard to keep stable. This is an outdoor measurement. And about 575 ppm of carbon dioxide. These are ambient levels. And if you see, the fits are very good. This uses 1F WMS. This uses 2F WMS, just to show that both approaches work using our technique. And the sensitivities are also very good. The sensitivities are at par with the sensitivities that are prescribed by the regulatory authorities. And please bear in mind that this is single pass measurement. If you wanted to do multi-pass, these sensitivities would scale accordingly. So that gives us a very solid, a lot of confidence that this method works reliably, not in the laboratory, but outside the laboratory in an open setting. What is also very pleasing for us to note is that this method works very nicely in congested spectra. So here is water vapor, ambient water vapor, where normally we would target this absorption line as shown here, avoiding this one because there is a smaller line on the shoulder. But when we apply this technique, it is possible to use such lines that have spectral congestion because the lasers, the spectral wings are not important in our measurements. You've extracted everything from the output of the laser itself. So you're not extracting anything from the gas absorption line. We've also applied this to other types of lasers, as you see, and the method works really nicely. So in conclusion, we would say that this technique is working very reliably. We would prefer to use 1F WMS because it's much stronger than the 2F. But in case 2F is necessary to avoid the background, this would work equally well. It's easy to implement because you are simply digitally filtering out the output of your laser. You don't need access to both ends of you don't need access to the spectral wings. You don't need to pre-characterize the laser. And you can use the same technique for the different kinds of lasers that are widely used. The single pass detection is what we've shown you. It works for congested spectra as well. And so we believe that there's a lot that we can do with this technique that we've recently developed. And we hope to apply this technique to the other fields in which our lab is also active. Some pictures of the real life setting in which these measurements were done This is a faraway place from here. The system goes and sits there for a week, does measurements, comes back to the campus and does measurements. So we're able to compare the urban measurements with the background measurements in remote places. So we believe that we are in a good position to contribute to this kind of measurements. And thank you for your time. And I'm happy to take any questions that you may wish to direct to me. Here is my email address. Thank you once again to the audience and to the organizers for kindly giving me the opportunity to present our work. I'd be very happy to be in touch with you, with the community. Thank you.